Good morning, everyone. Welcome back. Thank you for joining us. We're glad that you're here. I'm Steve.
And I am Scott.
Together, we're Backyard Musing, Science and Technology channel.
Yep, and we're talking about another space topic this morning, and involves our favorite telescope, the James Webb Space Telescope. And here we go.
A bizarre ultralight planet is cloaked in such a thick haze that even the James Webb Space Telescope can't reveal its composition.
I can't believe that.
Gosh, I know. Its unusual size and orbit are forcing scientists to rethink how planets form. A newly published study in the Astronomical Journal dated March 16, 2026 suggests that a dense haze surrounding the ultra-low density planet Kepler 51d, again, D means the fourth planet from its sun, may be concealing both its composition and how it formed. Would you like to know more?
Very secretive. Researchers led by Penn State used NASA's James Webb Space Telescope to investigate this unusual super puff planet, which already challenges standard models of planetary formation. What they found added to the mystery. The haze enveloping the planet appears to be the thickest ever observed, making it extremely difficult to detect the chemical signatures in its atmosphere and uncover clues about its origin.
Kepler 51 is a star about 2,615 light years from Earth in the constellation Cygnus. It hosts 4 known planets, at least 3 of which are classified as superpuffs. These worlds are roughly the size of Saturn, but contain only a few times the mass of Earth. Among them, Kepler 51d is both the coolest and the least dense.
2,615 light years. That's a ways.
That's a ways.
Yeah. Quote, we think the 3 inner planets orbiting Kepler 51 have tiny cores and huge atmospheres, giving them a density akin to cotton candy, said Jessica Libby Roberts. That's Jessical, Jessica. And she's from the Center for Exoplanets and Habitable Worlds postdoctoral fellow at Penn State at the time of the research and first author of the paper. Going on with her quote, I'm going to assume it's her. These ultra-low density superpuff planets are rare, and they defy conventional understanding of how gas giants form. And if explaining how one formed wasn't difficult enough, this system has 3 exclamation points. So
yeah, in most cases, gas giants form with solid, dense cores that create strong gravity, like Jupiter, allowing them to pull in and retain thick envelopes of gas. These planets typically develop farther from their stars, where gas is more abundant, similar to Jupiter and Saturn, beyond the asteroid belt. Kepler 51d does not follow this pattern. It appears to lack a dense core and orbits its star at a distance similar to Venus's position relative to the sun. Wow.
Yeah. Quote again. Kepler 51 is a relatively active star, and its stellar wind should easily blow away the gases from this planet, though the extent of this mass loss over Kepler 51d's lifetime remains unknown. That's according to Libby Roberts, who is now an assistant professor of physics and astronomy at the University of Tampa. So she's relocated. So going on with the quote, it's possible that the planet formed further away and moved inward, but we are still left with a ton of questions about how this planet and the other planets in the system formed. What it is about this system that created these 3 really oddball planets, a combination of extremes that we haven't seen anywhere else. Interesting.
Because these planets are so low in density, researchers think they're dominated by light elements such as hydrogen and helium, along with other materials. Identifying those elements would provide important clues about where the planet formed and the conditions it experienced.
Although Kepler 51d cannot be directly imaged, scientists can study it by observing its host star. When the planet passes in front of the starlight dims slightly and filters through the planet's atmosphere. We talked about another planet or asteroid or something, or moon that did that too.
Yeah,
I forget.
That's how they observe these. Yeah.
Yeah. Quote again, a star's light is filtered through the atmosphere of the planet before it reaches our telescopes. And again, that's back to Libby Roberts. Going on with the quote, if a certain molecule is present in the atmosphere that absorbs a certain wavelength of light, like how different colored objects on Earth absorb different wavelengths of light, it can block the light at that wavelength. If we look across a range of wavelengths across a spectrum, we get sort of a fingerprint of the planet's atmosphere that reveals its composition, unquote.
Yeah, so like how the ocean is blue, that's reflected from the atmosphere. So that's kind of
right.
principle the same.
Yep.
Earlier observations using NASA's Hubble Space Telescope examined near-infrared light between about 1.1 and 1.7 microns. James Webb Space Telescope's more advanced near-infrared spectrograph extended this range to 5 microns, which should have revealed more detailed features of the atmosphere. Instead, researchers found no clear absorption signals.
Yeah, and we do mention the Hubble Space Telescope every once in a while, and we like it too, but the James Webb is my favorite. So, the team also evaluated whether rings could explain the observations. If the planet had rings tilted at a certain angle, they might block starlight and make the planet appear larger and less dense than it actually is. However, this explanation does not match the observed pattern of light.
Further studies of similar planets could help clarify what is happening. Another team is currently analyzing James Webb Space Telescope observations of Kepler 51b to determine whether all super-puff planets share similar hazy atmospheres or if 51d is an exception. Fascinating. Fascinating.
So don't believe or think you're looking at everything that you see. You know, it could be different. Maybe different at a different angle, different haze. Interesting. But that they can do this so far out in space is just amazing to me.
I know.
And Baba.
It's our producer.
Mike.
All right, folks. Thanks for joining us. We'll see you in the afternoon.
We'll take care. Thanks. All right.
Okay.